Aloha, Richard Halverson here. This is ICS211, and today we're going to go over, we're in chapter 19, and we're going to go over binary search tree, the rest of the binary search tree chapter. So let me share my screen. All right, so we have covered up to section 19.6 in previous videos. So you can go check the playlist. And so today we're just going to finish up here. You know, these chapters really are a lot better if you read them slowly and closely, pay attention yourself, because if I start talking, I might lead you down a path that may confuse you more. But let's just go over these. The in-order traversal you'll need to learn because you need to implement it in your next lab. Let me just quickly show you in this lab assignment number 4. You need to implement in-order traversal, get height, and you got to come up with a node count method to add to the binary search tree class. So this is in-order traversal, and the tree traversal algorithm visits all nodes in the tree once and performs an operation. And on each node, the operation in our case is we're just going to print it. You know, in another application, you might be doing more, making some adjustments or something. But the in-order traversal visits all nodes in the binary search tree, smallest to largest, which is useful, for example, to print the tree's nodes in sorted order. See, what does it look like presenting? Okay, so in-order traversal visits all nodes in a binary search tree from smallest to largest. This is what the algorithm looks like. It's very, very simple. It's going to go, it's a depth. If there's, okay, so it enters a node. If it's null, it just returns. In other words, if you call it if you're at a leaf and you call it on a null child, let's say that this would happen. Otherwise, if there is a left node, you traverse that left node. You don't do anything with the current node. You traverse the left node. You keep on going left until you can't go left anymore. And then you do what you need to do to the node. You print the node in this case. And then you travel down the right and you do the same thing. So this is a recursive program. And you can see here, for example, it's going to, this is in alphabetical order. So it's going to start here. It's not null, so it's going to go to here. It's going to go down to here, and then it's going to go down to here, and then it's going to try to do this one. It's not there, so this thing happens, and then it returns up to here, and it prints that, and then it goes down here. Nothing happens, and then it returns. It's done going down with the right, so it returns back up to who called it. It was B. It was when we were looking at B when we called A, so that returns up to B. So A is printed, we go up to B, we print B, and then we go down to C, go down to here, both null, then we print C, and then we return, and we're done with B going to the right. We're done with this going to the right, so we go back up to D, and we're returning from B. When we are in D, we have just returned from visiting B, so we're back up here, and so we print the node, and then we go down the right. Anyway, so that's printing in order. Height is a little bit different. It's sort of the same. Here you just go left and right, but you ask the height of the left node. The left node doesn't know what height it is at, until it figures out what the height is of each of its children node. So we go all the way down to the bottom, just like with the in-order traversal. We could go all the way down to the bottom until we're down here, and this is going to be asking a child, a null child of a node, what its height is, and it's going to return -1 because it's not even a node, so it returns -1. This is where it returns it. It's going to either return it here, it's going to come up here or it's going to come up here. Or they both will. This is going to be the height of the left tree, if there is one. This is the height of the right tree, if there is one. And then this takes the maximum of the left and the right and adds 1 to it. So it figures out that this down here is height -1. This down here is height 1. And then we add, so this is height 0, add 1, this is height 1, this is height 2, and this is height 3. So this traces it through. Click through this to make sure you fully understand it. All right. Keeping track of parent node pointers is especially useful, especially if you want to do more recursion, searching through the tree. So this section here shows you how you can keep track of parent node pointers. A balanced binary search tree, such as an AVL tree. AVL is named after its creator, and then a red black tree. Do we cover those at all? I think I cover them a little bit in here somewhere. Anyway, you can look it up on the internet. It may utilize the parent pointer to traverse back up the tree from a particular node to find a node's parents, grandparents, or siblings. The BST insertion and removal algorithms below insert and remove nodes containing parent pointers. So when you have parent pointers for inserting a node, you can go through this and see how it works. You gotta make sure the parent pointers are set when you insert a node, and same with removing. You need to make sure the parent nodes are set. So here's BST removal, remove key and remove node algorithms. So you can go through this. It's better if you just go through instead of my trying to explain it and confuse you. This makes sure you understand it. BST will not work if the tree's root is null. So go through these to make sure you understand them. I don't want to confuse you more. Okay, so these are more recursive versions of the algorithms that we've just covered in this chapter. They all seem to have a little bit of recursion in them. They all call themselves, but this is utilizing the parent pointers. You can do much more in the recursive call. So the BST search can be implemented using recursion. A single node and a search key are passed as arguments to the recursive search function, and the 2 base cases exist. The first base case is when the node is null, in which case null is returned. If the node is not null, then the search key is compared to the node's key, and continues on. The second base case is when the search key equals the node key, in which case the node is returned. Anyway, so go through this, and here's this is the search program. It begins by calling the search recursive, looking for this key, starting with the root, and if the node is not null, it checks to see if the node is null, it returns null. If the node is not null, it first checks to see if the node that it is at has the key value it's looking for. If it does, it returns it. Otherwise, if the key value is less than the key value at the node, it searches the left tree. Otherwise, it searches the right tree. So go through this, see what the call stack looks like. Let's see, this is how many calls to BST search recursive are made by calling BST search 71? Well, it's this one here. It looks like I've done these already. So it's going to call it for 50. Going to call it for 75, and it's going to call it for 71, I guess. All right. So go through these and make sure you understand them. This is how you can get at the parent of a node, which is useful. Here's recursive insertion and removal. And for insertion, you just traverse down the tree until you find a null child. If the parents left is null, okay, so this is for inserting. It traverses till it finds an empty child, a null child link, and then it's able to insert it there. For the remove case, it's actually a little bit easier than in the previous remove, because you basically just search until you find the node you're going to remove, and then you search from there. You find the successor node, and then once you find the successor node, you remove the successor node, and you replace the node that you found. You replace the data in the node that you found that you can remove. The node that you can remove, you take the successor node's data and you put that into the node you're going to remove. You're actually removing the successor node, but you're taking that information in the successor node, putting it in the node that you're being asked to remove by the key or by the node here. And so that ends up being a little bit easier because you don't really have to do a lot of unlinking and so on. All right, so that's so go through this, and that takes us to the last one here is this Java binary search tree. And you should go through this because you are actually going to implement this in lab number 4. So this is what the node class looks like. Of course, the binary search tree class looks like this. You can complete this. The search method looks like this. If it finds the desired key, it returns it. Otherwise, it traverses down the left or traverses down the right. Here's the this is the search tree method. This is the insert. Searches until it finds an empty place to put it. Here's the program to test the search, test the insert and search methods with some data. So go through this binary search tree remove method. Now, you don't really have to understand this completely to be able to implement, because it's all there for you, but it's a good idea to go through this and understand what's going on. That's the kind of what you're supposed to learn out of this course. So go through and understand if node 750 is removed, which case is applicable. Oh, we're talking about the cases up here. And here's the code I'm asking you to implement in this lab here. Binary search tree lab, implement the binary search tree example here. That's this one. And there's the demo program, there's the node class, there's the binary search tree, which you're going to have to add. You're going to add 3 methods to this class right here, and then this is this print method that they give you. It's actually copyrighted and so on, I think. Anyway, so when you run this, this says this is the data. Let's see what this does. So this loads it up into a binary search tree, and then it's going to remove 5. And once it removes it, the binary search tree changes. Anyway, so yes, you're supposed to implement that here. And I give you lots of data to run it on. This is a 64 element random array. Got a bunch of them here. You're supposed to see how they work and run this. And so that I've completed, I'm pretty much finished with chapter 19. And so it concludes with a lab to help you understand how a binary search tree works. You're going to be if you if you become a computer scientist after graduation, and you're undoubtedly gonna come across the binary search tree data structure in your coding future. Very useful. Thanks for watching.